When you gaze up at the night sky, you are seeing light that has traveled many years, sometimes many centuries, across the vastness of space to reach your eyes. Each star twinkles with ancient light. In fact, some of the starlight you see tonight began its journey long before you were born, even before humans invented the tools to notice it. As you relax under the stars, imagine those light photons quietly crossing trillions of miles for years and years, until finally gently ending their journey here on Earth, just to softly illuminate your night. It's a reminder that the cosmos is older and larger than we can truly fathom, and by the time its light reaches us, we are peeking into the distant past. There are more stars out in the universe than there are grains of sand on all the beaches of our world. Just picture a handful of sand, so many tiny grains, then imagine every beach and desert on Earth. The number of stars in the cosmos far exceeds even that. It's a comforting thought, in a way, realizing how abundant the stars are. The sky above is filled with uncountable suns, each one a distant star glowing softly. Whenever you feel alone, you can remember that in the dark expanse overhead, there are countless stars quietly shining, more than every grain of sand between your toes on a warm beach. On a clear, dark night far from city lights, you might notice a pale, milky band stretching across the sky. This is the Milky Way, our home galaxy, seen from the inside. What looks like a misty cloud is actually the combined glow of billions of distant stars all together. We live within this vast starry collection. The Milky Way encircles us like a great starry river. When you see that soft ribbon of light, you're looking edge-on into our galaxy's dense starry disk. It's a gentle reminder of how immense our galactic home really is, filled with stars too numerous to count, all blending their light into a delicate band across the sky. Our Milky Way galaxy itself is enormous, stretching about 100,000 light-years from end to end. If you could travel at the speed of light, it would still take you 100,000 years to go from one side of the galaxy to the other. Within this vast disk, hundreds of billions of stars are drifting in a slow cosmic dance. Our Sun is just one humble star among them. The galaxy slowly rotates, taking roughly 230 million years to turn once so leisurely that from our perspective, the sky seems almost unchanging. Knowing the sheer scale of our galaxy can feel humbling, but also peaceful. We are cradled inside something so much larger than ourselves, moving calmly through the cosmos. The nearest large galaxy beyond our Milky Way is called the Andromeda Galaxy. It's so far away that its light takes 2.5 million years to reach us. When you look at the Andromeda Galaxy, visible as a faint smudge of light, if you know just where to look, you are seeing it as it was millions of years ago. At that time, early humans did not yet exist. Now, after its long journey, that gentle glow from Andromeda meets your gaze. In the still of the night, it is astonishing to realize that your eyes can catch the faint light of an entire galaxy, one that has been traveling through space for so long. It's a quiet connection across an almost unfathomable gulf of space and time. The Andromeda Galaxy and our Milky Way are on a slow collision course, moving toward each other through space. But there's no need to worry. This cosmic embrace will happen about 4 billion years from now. When it does, it will be a very gradual, silent event unfolding over millions of years. The galaxies will pass through one another, their stars mingling like two gentle swarms of fireflies merging. Eventually, they will form a single larger galaxy that some call Milkomeda. For now, Andromeda is a tranquil companion in our sky, and the thought of our galaxies meeting in the far future is a reminder of the slow, grand ballet of the universe. Even when galaxies like the Milky Way and Andromeda collide, the individual stars inside them are so far apart that they almost never hit each other. Imagine two clouds of birds merging. The flocks combine, but the birds themselves have plenty of space. In the same way, when our galaxies merge billions of years from now, our sun and planets will likely drift gently into the new cosmic arrangement without colliding with other stars. The vast distances between stars mean that even a galactic collision is more like a peaceful mixing than a violent crash. It's a comforting thought that in the immense spaciousness of galaxies, things can interweave so serenely. On an especially dark night in the right conditions, our unaided eyes can actually see a few of those distant galaxies beyond the Milky Way. The Andromeda galaxy, for one, can be spotted as a faint oval glow. In the southern hemisphere, observers can admire the Magellanic Clouds, two small neighboring galaxies of our Milky Way, as fuzzy patches in the sky. In total, from Earth we can see only a handful of galaxies without a telescope. Each appears as a tiny blur of light, yet each blur contains billions upon billions of stars. Knowing these delicate smudges, our entire galaxies can fill you with wonder, but the view itself is softly unimposing, just a gentle reminder of the universe beyond, visible if you look carefully into the quiet night. While these far-off wonders slowly move and evolve, our own Earth is no slouch. It's constantly in motion too. Earth spins on its axis, turning us toward the morning sun, and then into night, over and over in a reassuring rhythm. At the same time, Earth is also orbiting around the sun, carrying us through space along an invisible path. Even as you lie still, listening to this, you are on a spinning planet, hurtling through space. Yet all this motion is smooth and steady, a cosmic ride we all take together. It's a bit like being on a calm, constantly moving carousel that we never even notice. The speeds involved in Earth's motion are astonishing, though we don't feel them. Right now, if you are near the equator, you're moving with Earth's rotation at roughly 1,000 miles per hour, about 1,600 kilometers per hour. Meanwhile, Earth carries us around the sun at about 67,000 miles per hour, 107,000 kilometers per h. These numbers sound extreme, but because the motion is steady and unchanging, everything feels still and quiet to us. It's like gliding on a perfectly smooth train, constant motion, yet serenely imperceptible. This gentle motion is a reminder of how gracefully nature can carry us along, traveling vast distances through space, while we comfortably go about our lives, unaware of the speed. Our moon, Earth's faithful companion, is locked in a kind of gentle embrace with us. It's what's called tidally locked, meaning the moon turns on its axis in the same amount of time it takes to orbit Earth. Because of this, the same side of the moon always faces us. Whenever you look at the moon, that familiar face with its dark patches and bright craters, you're seeing the side that has always gazed back at Earth for millions of years. The moon itself is silently spinning, but in such perfect harmony with its journey around Earth that we never see the other side without sending spacecraft to look. It's a steady, predictable dance that has persisted through all of human history, contributing to the moon's tranquil presence in our sky. The moon's presence has a gentle influence on our Earth. Its gravity reaches out and tugs subtly on our planet, stirring the oceans. This is what causes the ocean tides. As the moon orbits us, its gravitational pull causes the water on the Earth to bulge slightly both on the side closest to the moon and the side farthest from the moon. As Earth rotates each day, these bulges sweep across the globe, and we experience them as the regular rise and fall of sea levels, high tide and low tide. It's a very gradual and calm movement of water on a planetary scale. Next time you walk along a beach and see the waves creeping higher or retreating, you're witnessing the moon's gentle goodnight kiss to Earth, drawing the oceans ever so softly. Our moon is slowly drifting away from Earth. Each year, It moves about an inch or two farther into space, roughly the rate at which your fingernails grow. This gradual separation is caused by the subtle transfer of Earth's rotational energy to the Moon. Over millions of years, this will slightly lengthen our days and make the Moon appear smaller in the sky. But rest assured, the change is so slow that many millions of nights will pass before any noticeable difference occurs. In the meantime, the Moon continues to circle us, a little further away each year, in a serene and unhurried retreat that will take billions of years to significantly change our view. If you ever see photos of footprints on the Moon left by astronauts, it's amazing to realize those imprints might last for millions of years. The Moon has virtually no atmosphere, no wind or rain to erode them. When the Apollo astronauts stepped onto the lunar surface, the dust compressed under their boots, and since nothing on the Moon quickly wipes marks away, those prints remain frozen in time. The silent lunar surface preserves each footprint, each track of the rover, almost exactly as it was when first pressed into the ground. In the stillness of the Moon, change comes slowly, so in the moonlight you can imagine those footprints quietly waiting, untouched in the silence, perhaps until humans visit again, or far, far longer. Mercury, the closest planet to the Sun, is a world of extremes. A single day on Mercury, meaning one full spin on its axis, is very long compared to its year. Mercury rotates so slowly that from one sunrise to the next on Mercury takes 176 Earth days. That means if you lived on Mercury, the sun would rise, and it would be roughly half of an Earth year before it set again. During that long day, the side of Mercury facing the sun becomes incredibly hot, while the long night is bitterly cold. This slow turning gives Mercury a strange, gentle pacing. The little planet takes its time to greet the dawn. Mercury's rotation has a special rhythm with its journey around the sun. The planet spins exactly 3 times on its axis for every 2 orbits it makes around the sun. This is called a 3-2 spin orbit resonance. It means that Mercury has what might be thought of as 2 days every 3 of its years. This precise cosmic timing is like a waltz between Mercury and the Sun. It's fascinating to imagine this small planet, closest to the Sun's glare, locked in such a steady pattern, a slow repetitive dance in the scorching sunlight, perfectly balanced by nature's clockwork. Our neighboring planet Venus has a peculiar way of spinning, almost opposite to most other planets. If you could hover above Venus's north pole and watch, you'd see Venus turning clockwise, backwards, whereas Earth and most others spin counterclockwise. On Venus, the sun rises in the west and sets in the east, the reverse of what we experience. This retrograde spin is gentle and very slow. In fact, Venus rotates so slowly that a day on Venus, one full turn on its axis, takes longer than its entire year orbiting the Sun. It's as if Venus decided to take a languid spin in the opposite direction, in no hurry at all. To put into perspective how slow Venus's spin is, it takes about 243 Earth days for Venus to rotate once, which is longer than the roughly 225 Earth days Venus takes to go around the Sun. So if you lived on Venus, the time between sunrises would be longer than a whole year. This means you'd see only one sunrise, if you could see the Sun through Venus's thick clouds in that entire time. Such a slow rotation gives Venus an unhurried lingering day and night cycle. Under its perpetual cloud cover, the planet turns ever so slowly, making a Venusian day a drawn-out mellow affair. Despite being farther from the Sun than Mercury, Venus is the hottest planet in our solar system. The reason lies in its atmosphere. Venus is wrapped in a thick blanket of carbon dioxide, with clouds of sulfuric acid, creating a powerful greenhouse effect. Heat from the Sun gets in but has a hard time getting back out. As a result, Venus's surface stays around 465 degrees Celsius, over 860 degrees Fahrenheit everywhere, day or night. It's a dry pressure cooker heat. We wouldn't survive in that environment, but thinking about it from afar, you can picture a world perpetually warm and still, its surface hidden beneath yellowish clouds. It's a reminder of how different other worlds can be. Venus is like an oven wrapped in fog, quietly baking for eons. Earth, our home, has a name unlike any other planet in our solar system. All the other planets were named after ancient gods and goddesses, Mars after the Roman god of war, Venus after the goddess of love, and so on. Earth's name simply means the ground or the land in old languages. It's humble and homey. No matter what we call it, our planet is special in many ways. It's the one place we know of that teems with life and comfortable oceans and air. As you lie back on Earth's surface and stare up at the cosmos, you're doing so from the only world we know that can cradle life so gently. Earth is cocooned by an invisible magnetic field that shields us from harsh space radiation. High-energy charged particles flowing outward from the sun, the solar wind, are deflected by this magnetic field, enveloping our planet like a protective blanket. When some of these particles do stream down into Earth's upper atmosphere near the poles, they set off shimmering lights in the sky. These are the auroras, the northern and southern lights. If you've ever seen pictures of those soft, colorful curtains of light dancing in polar skies, know that it's Earth's way of gently glowing under the touch of the sun's particles. The auroras wave slowly and silently, a beautiful ethereal display that is the night sky's own subtle lullaby, powered by our planet's connection to the sun. Mars, often called the Red Planet, has a day remarkably similar in length to an Earth day. A Mars day, or so, is about 24 hours and 39 minutes long. So if you were living on Mars, your day-night rhythm would feel almost like home, just 39 minutes longer. Each morning on Mars, the sun would rise over rust-colored deserts and dusty hills, taking only a slightly longer time to come around again than it does on Earth. This familiarity is comforting. Even on another planet, the cycle of day and night would march on in almost the same gentle cadence we know so well. A year on Mars, however, is a different story. Because Mars is farther from the sun, it takes about 687 Earth days to complete one orbit. That's almost 2 Earth years. With the day nearly the same, this means there are about 668 Martian days in a Martian year. Seasons on Mars last about twice as long as those on Earth. As you drift off to sleep, imagine the slow change of Martian seasons, spring, summer, autumn, winter, each stretching on and blending softly into the next, over almost 2 Earth years per cycle. Mars moves around the sun in a leisurely way, taking its time to journey through the Martian year. Strange as it may seem, sunsets on Mars are blue, while daytime Mars has a butterscotch or orangey sky from all its fine dust. The dust actually causes the light of the setting sun to disperse in a way that turns the area around the sun blue as it dips below the horizon. So on a Martian evening, the last light of day would glow a cool blue color, fading into the night. It's a gentle, beautiful contrast, the rusty daytime sky giving way to a calm blue twilight. Even on a planet so different from our own, there's poetry in a sunset. You can almost picture standing on the Martian plains, the quiet desert stretching out, as the sky performs a soft blue farewell for the day. Looming beyond Mars is Jupiter, the giant of our solar system. Jupiter is absolutely enormous, more massive than all the other planets combined. You could fit over 1,000 Earths inside Jupiter's volume. Despite this immensity, from here Jupiter appears as a bright, steady star in the night sky, a serene pinprick of light. On Jupiter itself, everything is on a grand scale. It's a vast sphere of gas, with subtly banded clouds stretching around the entire planet. To imagine Jupiter's size, think of the Earth as a small apple and Jupiter as a beach ball. That's roughly their size difference. Jupiter's great bulk drifts in space, a gentle giant watching over the inner solar system from afar. One of the surprising things about Jupiter is how quickly it spins. A day on Jupiter, the time it takes to complete one rotation, is only about 10 hours. This means Jupiter is spinning more than twice as fast as Earth, even though it's so much larger. This rapid rotation causes Jupiter to bulge slightly at the equator and flatten a bit at the poles. But from our vantage point through a telescope, what we notice is that its clouds streak around quickly. If you could float in the Jovian atmosphere, you'd see the sun rise and set in just 5 hours each, with night swiftly giving way to dawn. The planet's rapid whirl gives it energy and dynamic weather patterns, all churning away quietly in the vacuum of space. Jupiter is famous for a colossal storm called the Great Red Spot, a swirling oval that has been observed for hundreds of years. This storm is like a hurricane that never fully calms. At its largest, it could fit 2 or 3 Earths side by side within it. Lately, astronomers have noticed the Great Red Spot is slowly shrinking. It's still huge, but not as wide as it used to be. Even so, it remains a persistent, mesmerizing feature. Imagine a gentle red swirl persisting century after century, slowly changing, in the endless atmosphere of Jupiter. It's a bit like watching an eternal storm from a great distance, one that has been ongoing since long before you were born, and will likely continue long after, steadily churning in Jupiter's tranquil-looking visage. Jupiter's tremendous size and gravity influence the solar system in subtle ways that actually benefit us here on Earth. Acting like a big sibling, Jupiter's gravity often pulls in or deflects wandering comets and asteroids that might otherwise come closer to the inner planets. In this way, Jupiter serves as a sort of cosmic guardian. Over the eons, its presence has reduced the number of large objects that hit Earth. As you rest, consider that far out there, Jupiter is silently taking on some of the hazards of space. It's comforting to think that this giant planet, shining as a bright dot in our sky, is also one reason our own planet has been a relatively safe harbor for life over billions of years. Jupiter isn't alone out there. It has a whole entourage of moons, more than 70 of them known, like a miniature solar system. 4 of these moons are so large and interesting they're called the Galilean moons, after Galileo, who first observed them with his telescope. One of them, Ganymede, is larger than even the planet Mercury. Another, Io, is dotted with hundreds of active volcanoes, constantly reshaping its surface. Europa, coated in ice, likely hides an ocean beneath its frozen crust, and Callisto is a heavily cratered ancient world. Each moon is a unique silent world circling the giant planet. In a telescope, they appear as tiny points lined up near Jupiter. It's peaceful to think of all these moons gliding around their giant primary, engaged in their age-old orbiting dance around Jupiter. Further out, adorned with its breathtaking rings, lies Saturn. Saturn is another gas giant, only slightly smaller than Jupiter, but it wears the most sublime set of rings. Through a small telescope, those rings make Saturn look like a delicate ornament hanging in the sky. The rings are made of countless pieces of ice and rock, some as small as pebbles and others as big as houses, all orbiting Saturn's middle in a flat plane. They catch sunlight and shine, making the planet appear especially majestic. Saturn has a serene pale golden glow when seen from Earth, a gentle giant with a gossamer halo. In the stillness of space, Saturn carries its beautiful rings with it, an ever-present reminder that even in the quiet expanse, artful wonders exist. Saturn's rings may span hundreds of thousands of miles in diameter, but they are astonishingly thin, only tens of meters in some parts. Imagine a sheet of paper the width of a city, that's analogous to how thin Saturn's rings are relative to their size. They might look solid from afar, but if you were among them, you'd see mostly empty space between particles. The ring particles orbit in nearly perfect balance, shimmering as they catch the light. The thinness of the rings is part of what makes them so delicate and transient. Over millions of years, the rings may change or even dissipate,
but for now they are one of the loveliest sights in our solar system, quietly encircling Saturn like a cosmic whisper. Saturn is a gigantic planet, yet it's also very light for its size. It's less dense than water. This leads to a famous imaginative scenario. If you could find a bathtub big enough, Saturn would float in it like a huge ball of lightly packed ice. Of course, such a bathtub doesn't exist, but the idea captures how Saturn, with all its mass, is mostly made of gas and is spread out so much that it's not very dense. It's as though Saturn is a great celestial cloud, substantial yet buoyant. Picturing that can give you a sense of how gentle this giant is. Despite being enormous, its composition is airy enough that it wouldn't sink in water. This softness of Saturn's nature is another calming thought, as it drifts in its orbit, quietly poised in the darkness. Among Saturn's many moons is Titan, a world that intrigues scientists and dreamers alike. Titan is larger than the planet Mercury, and shrouded in an orange haze. It has a thick atmosphere like early Earth might have. Beneath those clouds, Titan has rivers, lakes and even rain. But it's far too cold for liquid water. Instead, these rivers and lakes are made of liquid methane and ethane, substances that are gases here on Earth, but flow as liquids on Titan. Imagine standing on Titan's surface with a warm suit on. You might see a smoggy golden sky, and perhaps a dim sun. The landscape could remind you of Earth in a strange way, with rolling dunes or pebbled shorelines by cold, dark lakes. Titan slumbers in the outer solar system, a cold moon with a surprisingly dynamic and Earth-like geology, all unfolding slowly under its perpetual twilight skies.
Another moon of Saturn, Enceladus, is a tiny, bright gem. Enceladus is covered in ice, and it reflects sunlight almost like fresh snow, making it one of the most reflective bodies in the solar system. This means it stays extremely cold, far below freezing all the time. But Enceladus has a warm secret. It hides liquid water beneath its ice. We know this because Enceladus has geysers, great plumes of water vapor and icy particles that erupt from cracks near its south pole, shooting material into space. These geysers spray so high that they feed Saturn's rings with fresh ice particles. It's an incredible thought that on this little moon there are fissures where water from an underground ocean is constantly gently puffing out into space, like a hidden ocean breathing out into the void. Enceladus shows that even in the coldest corners there can be warm activity and possibly the conditions for life, quietly ongoing beneath an icy crust. Moving out to the next planet, we find Uranus, a pale blue-green world that does something very unusual. It lies on its side. Unlike any other planet, Uranus is tilted over so far that it essentially rolls around the Sun like a ball. Its axis is tilted by about 98 degrees. This means that for part of its long year, one pole points almost directly at the Sun, while the other is in darkness, leading to seasons unlike any we know. One pole has a 21-year-long day, while the other has a 21-year-long night, and then they swap. Despite this extreme tilt, Uranus turns once about every 17 hours, so it still has a day-night cycle even during those long seasons, but the Sun's path in the sky would be very strange. It might circle around near the horizon for decades. Uranus's sideways spin is a reminder that the cosmos isn't always uniform. Sometimes worlds have their own unique tilted grace. The color of Uranus is a delicate blue due largely to methane gas in its upper atmosphere. Methane absorbs the redder wavelengths of sunlight and lets the bluer light filter back out, giving Uranus that calm cyan hue. When you think of Uranus, imagine a serene blue-green orb softly glowing in the darkness, featureless to the casual glance as it quietly rotates on its side. There aren't prominent storm bands or spots visible most of the time, just a tranquil blue disk through a telescope. That steady hue and placid appearance make Uranus a rather soothing presence in the pantheon of planets, modest and unassuming in its distant orbit. Neptune, the farthest planet, lies even farther from the Sun, in a realm of deep blue. If Uranus's blue is pale and gentle, Neptune's is a richer, more vibrant blue. It's a dynamic world, with the fastest winds in our solar system. Despite the sunlight being so faint out there, only about 1/900th of what we get at Earth, Neptune's atmosphere whips up winds that can reach up to 1,500 miles per hour. These winds drive large, dark storm systems that come and go. One such storm, known as the Great Dark Spot, was photographed by Voyager 2 in 1989, then later disappeared. Neptune's weather is wild, yet from our far vantage point, the planet itself appears as a steady blue dot, serenely orbiting the Sun. The contrast between its calm appearance and the fierce winds beneath the clouds is another marvel of the silent void of space, where even tumultuous storms make no sound. A year on Neptune, one full orbit around the Sun, takes about 165 Earth years. Since Neptune was discovered in 1846, it has only made one full orbit in the roughly 179 years since. Seasons on Neptune last over 40 Earth years. Imagine a single spring that lasts 4 decades, followed by a summer that spans another 40 years. The changes are gradual and subtle at that distance. For any observer on Neptune, the Sun would be just a very bright star, providing only a dim twilight glow. The slow, long year of Neptune is a reminder of the vast scale of the solar system. Time and seasons stretching out quietly over human lifetimes, many times over, with the planet patiently circling the Sun far beyond our sight. Neptune has a moon named Triton that is particularly fascinating. Triton orbits Neptune in the opposite direction to Neptune's rotation, a retrograde orbit, which is very unusual for a large moon. This suggests Triton was likely a wandering object, perhaps similar to Pluto, that Neptune's gravity captured long ago. Triton is a cold, icy moon with geysers of its own, though instead of water, they likely shoot nitrogen gas. As Neptune slowly moves through its long year, Triton circles it every few days, but heading backwards, compared to the direction Neptune spins. This odd, backward dance marks Triton as an adopted child of Neptune, and the relationship has a dramatic future. Because Triton orbits Neptune opposite to Neptune's spin, gravitational forces are pulling on it in a way that is causing Triton to spiral inward, slowly but surely. Scientists believe that in perhaps tens of millions of years, a blink in geologic time, but a long time to us, Triton may come so close to Neptune that Neptune's gravity will tear the moon apart. If that happens, the pieces of Triton could spread out around Neptune and form a new set of rings, maybe even more spectacular than Saturn's. For now, Triton hangs in there, circling Neptune dutifully and silently, a cold world gradually succumbing to Neptune's embrace. The idea that one day Neptune might wear Triton's remnants as a necklace of rings is a melancholic yet beautiful image of cosmic recycling. Farther out than Neptune, in the dim reaches of the solar system, is Pluto, once considered the 9th planet, now classified as a dwarf planet. Pluto is an incredibly small world. Its diameter is only about 1,400 miles, 2,300 kilometers, which is about 2/3 the width of our moon. In fact, North America is wider than Pluto. If you were to lay Pluto on top of the United States, it would just about stretch from California to the middle of the Atlantic Ocean. Because of its size, Pluto's gravity is much weaker than Earth's. If you weigh 100 pounds on Earth, you'd weigh only about 7 pounds on Pluto. It's a chilly, tiny orb at the edge of our solar neighborhood, taking a slow 248 Earth years to make one trip around the Sun. Gentle sunlight, 1,000 times fainter than on Earth, bathes its frozen surface in perpetual twilight. Pluto might be small, but it holds a big place in our hearts as a distant, icy friend. Pluto has a companion named Charon, which is so large relative to Pluto that some call the two a double dwarf planet. Charon is about half Pluto's size. The interesting thing is that Pluto and Charon are tidally locked to each other. Much like how one side of our moon always faces Earth, one side of Charon always faces Pluto, and one side of Pluto always faces Charon. They present the same face as they rotate together, completing a turn every 6.4 Earth days. If you stood on Pluto, Charon would hover in nearly the same spot in the sky, not rising or setting but maybe just wobbling a bit. And if you stood on Charon, you'd see the same hemisphere of Pluto all the time. This pair dances around each other in a quiet synchronized twirl at the edge of the solar system, bound together by gravity and moving as one. The realm of Pluto is not empty. It's part of a larger region of space filled with other small icy worlds. Beyond Neptune's orbit lies the Kuiper Belt, a vast collection of frigid objects left over from the formation of the solar system. Pluto is one of the largest of these Kuiper Belt objects. Out there, the Sun is just a very bright star, and everything is cold and dark. Beyond the Kuiper Belt, even farther out, it's thought that a spherical cloud of comets, the Oort cloud, surrounds our solar system at an almost unimaginable distance, light years away. Every so often, one of these distant icy bodies gets nudged toward the inner solar system and becomes visible as a comet. Most of the time, though, they remain in deep freeze, slowly orbiting the Sun in the far, far quiet reaches of space. It's awe-inspiring to consider that our solar system has these distant outskirts, a sort of cosmic hinterland filled with ancient silent ice balls that have been orbiting undisturbed for billions of years. When one of those icy visitors from the outer solar system falls inward toward the Sun, we get the beautiful spectacle of a comet in the sky. Comets are often called dirty snowballs. They are mixtures of ice, dust, and rocky material. As a comet approaches the warmth of the Sun, its ice begins to vaporize and releases gas and dust. Solar radiation and winds push this material out into glowing tails that can stretch for millions of miles across space. From Earth, we see comets as faint, fuzzy stars with delicate tails sometimes visible to the naked eye. They appear slowly, change night by night, and then fade away again into the darkness. Observing a comet can be a meditative experience. This faint, otherworldly light has come from the cold edge of our solar system, putting on a gentle show in our skies before returning to deep space. The next time you see a picture of a comet, think of the quiet grandeur of this icy wanderer, developing a luminous veil as it glides near the Sun. One of the most famous comets is Halley's Comet, known for its predictable visits. Halley's Comet swings through the inner solar system about every 75 to 76 years, and it has been observed since antiquity. Every time it comes near the Sun, it sprouts its glowing tail and graces our sky for a short while. The last time was in 1986, and it will be back around 2061. It's soothing in a way to know that this comet keeps coming back like clockwork, a sort of celestial old friend making periodic visits through the generations. Marking the calendar for a comet that our children or grandchildren might see connects us softly with the future. In the vast clock of the solar system, Halley's Comet is one of the ticking hands, slowly measuring out human errors with its appearances. Between Mars and Jupiter lies the asteroid belt, often imagined as a crowded field of rocks tumbling and colliding. But in truth, the asteroid belt is mostly empty space. The asteroids are spread out over such a large volume that a spacecraft can fly through it and likely not encounter anything at all. The asteroids range in size from tiny pebbles to dwarf planets hundreds of miles across, but they are separated by huge distances.
If you were standing on one asteroid, the next nearest one might be so far away you could barely see it, if at all. This sparseness means that, contrary to the chaotic scenes from science fiction, the asteroid belt is a quiet, lonely place. Millions of rocks circle the sun, each solitary in its own path, rarely interacting. It's a calm and ancient region, remnants of the early solar system, continuing their slow solitary orbits. The largest member of the asteroid belt is a dwarf planet named Ceres. Ceres is about 590 miles, 950 kilometers wide, roughly the size of Texas. It was the first asteroid discovered, way back in 1801, and it's so sizable that its own gravity has pulled it into a round shape, earning it the dual title of asteroid and dwarf planet. Ceres is a cold, dark world, with evidence of water ice beneath its surface, and even the faint remnants of a vapor atmosphere at times. For billions of years, Ceres has orbited quietly between Mars and Jupiter, a little protoplanet that never grew into a full-sized planet. Now that we have sent a spacecraft to visit it, we know it has mysterious bright spots of salty residue in some craters, perhaps dried remnants of ancient briny water that welled up. Ceres, in its gentle orbit, holds clues about the dawn of our solar system, all while serenely continuing its journey around the Sun, each 4.6 years, as it has for eons. Every day, Earth is met by visitors from space, not large aliens or asteroids, but tiny dust and sand-sized particles that burn up in our atmosphere. In fact, it's estimated that tens of tons of meteoritic dust settle on Earth each day, sprinkled across the whole globe. Sometimes we see the larger of these small pieces as they streak through the sky, a quick bright flash that we call a meteor or a shooting star. But most are too small to notice. They drift down softly as microscopic specks that become part of our soil and oceans. This means that in a very gentle way, Earth is always collecting a little cosmic dust. As you breathe and relax, innumerable tiny motes from ancient comets and asteroids are floating down around you, unnoticed and harmless, joining our planet grain by grain, a subtle connection between us and the rest of our solar system that continues without sound or fuss. When you do see a shooting star streak across the night sky, know that you're witnessing a tiny piece of cosmic debris making a fiery final journey. That brilliant flash of light is typically caused by something no larger than a pebble, often just a grain of sand, entering Earth's atmosphere at incredible speed. The air friction heats it up and creates a glowing trail. Most of these burn up completely before they reach the ground. In those brief moments, they paint a delicate line of light across the sky for any lucky observer to see. It's a beautiful fleeting event, as if the universe were offering a little spark just for you before the night closes in again. Many cultures make a wish on a shooting star, a gentle recognition of the rare and wonderful sight of a grain of space dust burning like a tiny ember in our sky. Our Sun, the star that gives us daylight and warmth, is about 4.6 billion years old. It formed from a cloud of gas and dust that gently contracted under gravity, sparking into a nuclear fireball that's been shining ever since. The Sun is roughly halfway through its life. Stars like our Sun live for about 10 billion years before they change, so the Sun has about 5 billion years left in its current peaceful state. For us, 5 billion years is effectively forever. Countless generations will come and go under the same steady sunshine. Knowing the Sun is middle-aged but stable can be oddly comforting. Every sunrise you see is powered by processes deep within the Sun that have been reliably going on for eons and will continue for eons more, bathing our world in a gentle life-giving glow day after day. Eventually, in the very distant future, the Sun will grow into what's called a red giant. This will happen when the Sun runs low on the hydrogen fuel in its core and starts fusing helium and other heavier elements. The Sun will swell many tens of times its current size, and its surface will cool to a reddish color as it expands outward. Mercury and Venus will likely be swallowed up by the sun's expansion, and Earth, if not engulfed, will be scorched. This transformation is unimaginably far away, about 5 billion years in the future. While it's a dramatic fate, there's a gentle perspective to it. Everything in the universe has a life cycle, even stars. And just as surely as the sun rose for us this morning in its stable state, one distant day it will complete its life story. For now and for billions of tomorrows, it will continue to rise and set, a dependable warm light in our sky. The sun produces its energy deep in its core, through a process called nuclear fusion. It quietly fuses about 600 million tons of hydrogen into helium every second. In doing so, about 4 million tons of matter are converted into pure energy each second, according to Einstein's famous formula E=mc². This sounds like an explosive process, but to the sun it's a steady self-regulating burn that has gone on for ages. The energy released in the core slowly makes its way out, taking thousands of years to reach the surface, and then it radiates into space as the sunlight we feel on our skin. So when you stand in the sunshine, you are feeling energy that in a sense is the result of mass that vanished in the sun's heart long ago. The sun sacrifices a little of itself to keep us warm and lit. And fear not, even at that rate, it has more than enough mass to keep shining for billions of years ahead. Remarkably, the light we receive from the sun is ancient by the time it arrives. A photon, a particle of light created in the sun's core, may spend tens of thousands of years bouncing around inside the sun, zigzagging through dense plasma, before it finally escapes into space. Once free of the sun though, that photon races across the 93 million miles to Earth in just about 8 minutes and 20 seconds. This means when you see the sun, you're looking at it not exactly as it is right now, but as it was a few minutes ago. The difference is trivial for day-to-day life, but it's a gentle reminder that even light has a travel time. And the sunlight warming the late afternoon ground began its journey in the sun's core long before human civilization, taking a long leisurely ramble inside the sun, then a brief sprint across space, and finally arriving to brighten your day. To measure the immense distances in space, astronomers use the concept of a light year, not a measure of time, but of distance. 1 light year is how far light travels in 1 year, about 5.88 trillion miles, 9.46 trillion kilometers. It's a distance so vast it's hard to picture. Our minds might better grasp smaller units, so consider this: the moon is about 1.3 light seconds away. It takes light a bit over a second to get there. The sun is about 8 light minutes away. The nearest star beyond the sun is over 4 light years away. When we say a star is 100 light years away, that means its light has taken a century to reach us. These numbers gently emphasize how spacious our universe is. Yet thinking in light years also connects time and distance in a poetic way. To look far out in space is to look back in time, because we see objects as they were when their light started toward us. It's a reminder of both the vastness and the unity of space and time in our cosmos. The nearest star beyond our sun is Proxima Centauri, about 4.24 light-years away. That's roughly 25 trillion miles. Even the fastest spacecraft would take tens of thousands of years to reach it. Yet in the scale of the galaxy, Proxima Centauri is one of our closest neighbors. It's so faint that we cannot see it without telescopes, but it's part of a triple-star system called Alpha Centauri, which includes 2 stars similar to our Sun that you can see from the southern hemisphere. When you hear that distance, 4.24 light-years, and consider a light-year's immensity, it gives a very gentle perspective on just how far even our nearest stellar neighbor is. Still, in the grand starry night, 4 years at light speed makes Proxima close enough that its gravity very slightly affects our Sun's motion. Out of all those countless stars, it's touching to know that some are relatively near, quietly shining their own light that very slowly makes its way toward us across the void. Space officially begins about 62 miles, 100 kilometers above Earth's surface, at the Kármán line. Below this, the atmosphere is too thick. Above it, satellites can orbit without burning up from air resistance. Although there's no sharp boundary for where space begins, around that altitude the sky above turns from blue to black, and the air becomes almost a vacuum. It's astonishing. Space is just a short hop above our atmosphere. In about an hour's drive on a highway, if you could go straight up, you'd transition from the air we breathe to the silent, airless expanse of space. Knowing how thin our atmosphere is around the Earth can fill one with a renewed appreciation. A fragile, slender blanket of air is all that separates our comfortable life from the cold void. But that slender blanket is enough, and it's held in place by Earth's gravity, keeping us safe and warm under the vast cosmic ocean above. Humanity has built a permanently inhabited outpost in space, the International Space Station, or ISS, which circles around Earth at an altitude of about 250 miles, 400 kilometers. At that height, the ISS experiences very little atmospheric drag, and it orbits Earth every 90 minutes or so. Astronauts aboard see 16 sunrises and 16 sunsets each day. Life on the ISS flows in a unique rhythm. Work and sleep cycles are scheduled by clock, not by the sun, since the sun is rising and setting so frequently out the window. The station's path carries it over different parts of Earth each orbit. From the ground, if you know when to look, you might see the ISS as a bright, fast-moving star gliding across the early morning or evening sky. It doesn't blink like a plane. It shines with steady reflected sunlight as it quietly slips by. Knowing that there are people peacefully drifting high above, orbiting at over 17,000 miles per hour, can be a strangely comforting thought. Even in the silent emptiness, life finds a way to have a foothold, and those aboard the ISS gaze down on all of us, one world without borders, in the gentle vastness of night. If you ever get the chance to spot the International Space Station in the sky, you'll be witnessing human presence in space with your naked eyes. It appears as a bright, steady dot, usually rising in the west and setting in the east, since it orbits west to east to take advantage of Earth's rotation. There's no sound, of course. It's 250 miles up, moving silently through space, but it crosses the sky in just a few minutes. Many people find it moving to watch, some even give it a little wave, knowing astronauts are aboard. It underscores how small our world is in the context of space. A space station passing quietly above reminds us that we're all down here together on this blue planet, while a few explorers float in the calm darkness above, all of us sharing this moment of connection between Earth and sky.
Space itself, once you leave Earth's atmosphere, is utterly silent. Sound needs a medium like air or water to travel, and in the vacuum of space, there is no such medium. It's almost pure emptiness. This means that all the violent events we know are happening out there, exploding stars, crackling solar flares, colliding asteroids, occur in perfect silence. If you were spacewalking outside the ISS, you would hear only the sounds of your own breathing and perhaps your radio, nothing else. The silence of space is part of what makes the night sky so peaceful from our vantage point. We see immense fireworks of cosmic light, but none of the noise. Even a supernova, which would outshine an entire galaxy for weeks, would make not a peep in the vacuum. This profound silence can be a soothing thought. No matter how chaotic things may be, in space it all unfolds quietly. It's as if the universe is a grand silent movie, and we observe the visuals from our soundstage here on Earth. Life in space has some unusual effects on the human body. One gentle example is that astronauts often return to Earth a bit taller than when they left. In microgravity, the near weightlessness of orbit, the spine isn't compressed by the weight of your body as it is on Earth. The vertebrae relax and spread apart slightly. Astronauts can gain roughly 1 to 2 inches in height while living on the space station. Of course, when they come back down to Earth's gravity, their height returns to normal after some time. But it's interesting to think that in space, your body subtly stretches out, enjoying a relief from the constant pull of gravity. It's a harmless, even comforting change, the kind of stretch you can feel when you hang upside down for a bit, but sustained for months in orbit. This is one of many ways the human body adapts to life among the stars, softly and remarkably adjusting to a new environment. Another quirk of weightlessness is that astronauts can't burp the same way we do on Earth. Here, gravity helps keep solids and liquids in your stomach separate from gases, so a burp can expel just the gas. In microgravity, there's no easy way for the bubbles to rise. If an astronaut tried to burp, the result might be a bit of liquid coming up too, not a pleasant thought. So astronauts learn to be careful and patient with their digestive systems. They eat and drink in ways that minimize swallowed air. It's a small reminder that even everyday bodily functions are different in space. Imagine floating without up or down. Even your stomach feels the difference, and you adapt by doing things a little more gently. It's all part of the calm, careful life in orbit. When astronauts put on their spacesuits and helmets for spacewalks, they can't directly scratch their face if they get an itch. To help with that, there's a clever little addition inside the helmet, a patch of Velcro material. If an astronaut's nose tickles, they can rub or press it against the rough Velcro pad to get some relief. It's often fondly referred to as the nose scratcher. It's almost quaint that amid all the high-tech gear keeping astronauts alive in the vacuum, there's this simple, homey solution for a common tiny annoyance. Picture an astronaut drifting outside the station, Earth glowing blue below, and knowing that if their nose itches, they just nuzzle the inside of their helmet on a bit of Velcro. Even in the high adventure of space, it's those little comforts that remind us of our human side. The very word we use for space travelers, astronaut, has a poetic meaning. It comes from the Greek words astro, meaning star, and naut, meaning sailor. So astronaut essentially means star sailor, one who sails among the stars. The Russian term cosmonaut similarly means universe sailor. These terms capture the romance of exploration in a very gentle way, humans casting themselves into the cosmic ocean, sailing the void in their ships. It reminds us that space travel, for all its technology and danger, is also an act of exploration and serenity, like ancient seafarers journeying beyond the sight of land. Our star sailors today navigate by computers and thrusters, rather than wind and compass, but the spirit is the same. They carry our hopes and curiosities with them as they traverse the silent sea above. When we look out into the universe with our telescopes and our eyes, what we see, stars, planets, glowing nebulae, galaxies, is only a small fraction of what's truly there. In fact, only about 5% of the universe is made of the familiar matter that emits or reflects light like stars and planets. The rest is mysterious. About 27% of the universe seems to be made of something called dark matter. It doesn't shine or absorb light. We only know it's there because its gravity gently pulls on the things we can see. And roughly 68% of the universe seems to be an even stranger component called dark energy, which is pushing the universe to expand faster and faster. These unseen parts don't affect our daily life, but on the grandest scales they govern the motions of galaxies and the fate of the cosmos. It's humbling and oddly soothing to think that we are immersed in a universe where so much remains invisible and unknown. There is far more than meets the eye, yet it all holds together in a vast cosmic harmony that we are just beginning to understand. Dark matter, despite its somewhat ominous name, is really quite a gentle glue permeating galaxies. Imagine a galactic nightscape, billions of stars swirl within a spiral galaxy like our Milky Way. These stars move under the influence of gravity, But when astronomers measured how fast the stars at the edges of galaxies move, they found something puzzling. The outer stars were moving faster than they should if only visible matter were pulling on them. The solution was an unseen mass, dark matter, enveloping galaxies in a great halo. This dark matter doesn't clump into stars or planets, it drifts through and around galaxies, creating an invisible scaffold that holds them together. As you relax, envision our Milky Way floating in a vast halo of this transparent matter, like a subtle cocoon of gravity. We're gently cradled by it, even though we can't see or touch it. The stars are like glittering lights woven into a ghostly, invisible web of dark matter that extends well beyond the visible galaxy, keeping everything spinning together in a cosmic balance. Dark energy is even more enigmatic. In the 1990s, astronomers discovered that the expansion of the universe is not slowing down as expected, it's speeding up. This was a surprise, as the gravitational pull of all matter should be gradually slowing the expansion after the Big Bang. Instead, something is pushing galaxies apart more and more strongly over time, like a faint pressure inherent to space itself. They named this something dark energy. We don't yet know what dark energy is, perhaps a property of space, perhaps a new field or something else entirely, but we feel its effects on the largest scales. Over billions of years, dark energy will make galaxies recede from each other faster and faster. For now, in our corner of the universe, gravity still holds sway among nearby galaxies, and everything feels stable. Dark energy's influence is gentle on human scales. We don't notice it day to day, but it's an ever-present subtle force that shapes the destiny of the cosmos. Contemplating it reminds us that even in the quiet vacuum of space, there are still mysteries at work, silent and profound. In the heart of our Milky Way, and in the hearts of many galaxies, there lies a monster in peaceful slumber, a supermassive black hole. Ours is named Sagittarius A*, and it has a mass of about 4 million suns compressed into an area only about as wide as the distance from the Sun to Mercury. But despite the fearsome image black hole might conjure, for the most part, these supermassive black holes simply sit quietly. Stars orbit them at a safe distance, like planets orbiting a sun, and only the ones that venture too close risk any dramatic fate. Sagittarius A* is calm now. We detect it mainly by the way nearby stars whip around an invisible center. It's comforting to know that even something as exotic as a black hole can be a benign neighbor on cosmic time scales. It's only when material falls in that a black hole shows its power, often by flaring up as the material is heated. But otherwise, a black hole just is, a region of intense gravity silently existing. And at such a distance, 26,000 light-years from us, our galaxy's central black hole poses no threat to Earth, allowing us to study and wonder about it from a tranquil vantage point. A black hole, in essence, is gravity run amok. It is a place where a great amount of mass is concentrated in a very small area, resulting in a gravitational pull so strong that beyond a certain boundary, not even light can escape its grasp. That boundary is called the event horizon. Think of it as an invisible sphere around the black hole. If anything, say a star or a stray particle of gas, crosses that boundary, it vanishes from the known universe, drawn inexorably to the black hole's center. But outside the event horizon, if you observed from a safe distance, you might not even realize a black hole is there except by how its gravity affects the surroundings. They don't suck things in like a vacuum cleaner at large distances. Their gravitational pull follows the same rules as any other object of the same mass. So if the Sun were replaced by a black hole of equal mass, just a hypothetical, such a black hole would be only 6 kilometers across. Earth's orbit wouldn't change at all, we would just miss the sunlight. Thus, in a sense, black holes can be surprisingly gentle on their cosmic environment, unless you get very close. They are extreme phenomena, but they mostly sit quietly, their extreme nature hidden behind that mysterious horizon. In April 2019,
scientists released the first ever image of a black hole, a glowing ring of gas around the shadow of the black hole, at the center of galaxy M87 55 million light-years away. The photo was captured by the Event Horizon Telescope, a network of radio observatories around the world working in unison. It showed a fuzzy donut-shaped halo of light with a dark center. That dark center is the black hole's silhouette, where light is vanishing from view. That black hole is about 6.5 billion times the mass of our Sun, and the ring we saw was light distorted and heated to millions of degrees as it swirled in just outside the event horizon. Seeing it was a triumph of patience and ingenuity. As you hear about it now, think of the collaboration required, telescopes all over the world observing in harmony to catch the faint hum of photons orbiting a distant abyss. The image itself isn't sharp like a photograph, but it confirms that what we dreamed matches reality. Black holes exist as Einstein's equations predicted, and we can observe their edges. Even though a black hole itself emits no light, the universe allowed us this one indirect glimpse, as if pulling back the curtain just a little on its deep secrets. Black holes can have an almost whimsical effect on things that stray too near. Astronomers have a nickname for it: spaghettification. If a star or any object ventures too close to a black hole, the intense gravity can tear it apart in a process playfully called spaghettification, stretching the star into long streams of gas. The difference in gravity between the star's near side and far side becomes enormous, pulling it into a thin strand. It's a dramatic fate, but from a comfortable distance, we can find a bit of humor in the term. Thankfully, black holes are sparse, and these events are rare in the universe, and ours is a safe distance from anything like that. So while spaghettification might sound unsettling, it's not something we or any stars near us will ever experience. It remains one of those curiosities of extreme physics, nature's way of showing that truth can sometimes be stranger than fiction, in the most astonishing yet far-removed ways. Not all stars end up as black holes, only the most massive ones do. When a star much larger than our Sun runs out of fuel, it can no longer hold itself up against gravity. The core collapses rapidly, and the star's outer layers explode outward in one of the most powerful events in the universe, a supernova. For a short time, this dying star can outshine an entire galaxy. Then it leaves behind either a dense neutron star or a black hole, depending on its mass. But the supernova does something else incredibly important. It forges heavy elements and blasts them into space. Elements like gold, silver, iodine, and many others are created in those final moments of a massive star's life. The material from the star, now enriched with these elements, is scattered across space, ready to become part of new stars, new planets, perhaps new life forms. In a sense, a supernova is both an ending and a beginning, one star's violent end sowing the seeds for new growth in the galaxy, all unfolding in the silent vacuum with magnificent light but no sound, like a brilliant final chord we only see, not hear. When a very massive star goes supernova, sometimes the core that remains is so dense that it becomes a neutron star. This is essentially an atomic nucleus on a colossal scale. Imagine a ball about 12 miles 20 kilometers across, containing more mass than our Sun. In a neutron star, the matter is so compressed that a teaspoon of it would weigh billions of tons on Earth. It's an almost unimaginable density. These stars are like giant atomic nuclei, made mostly of tightly packed neutrons. They spin rapidly and have intense magnetic fields. The idea of something so heavy and so small is mind-bending, but these objects exist out there in the galaxy, the remnants of once brilliant stars that have burnt out. They're not dangerous to us, they're just exotic endpoints of stellar evolution, spinning quietly in the darkness. You can almost think of them as cosmic embers, extremely hot and dense, slowly cooling over eons after the fire of the supernova has gone out. Some neutron stars are especially charismatic. These are the pulsars. Pulsars are neutron stars that rotate extremely fast, some making a full rotation in fractions of a second, and they emit beams of radio waves or other radiation from their magnetic poles. Because the star is spinning, these beams sweep through space like the beam of a lighthouse. If Earth lies in the path of those beams, we detect a pulse of radio waves every time the beam sweeps by. That's why we call them pulsars. To a radio telescope, a pulsar's signals are a steady rhythmic ticking, on the order of milliseconds to seconds apart. When the first pulsar was discovered, its regular pulses were so precise that scientists humorously nicknamed it LGM-1 for Little Green Men 1, half-jokingly suspecting it might be a beacon from an intelligent civilization. But it was nature's doing, a rapidly spinning neutron star. These stellar remnants spin with extraordinary consistency. It's soothing in a way. Out there in space are these natural clocks, pulsing steadily for millions of years, an incessant calm ticking echoing through the cosmos, keeping time long after the star's visible light has faded. Not every star lives a short, bright life. The most common stars in the galaxy are actually red dwarfs, small cool stars that shine with a comparatively faint reddish light. Red dwarfs burn their fuel very slowly. A red dwarf star can live not just billions of years, but trillions. That's far longer than the current age of the universe, about 13.8 billion years. In fact, no red dwarf has ever died. The universe isn't old enough for one to have used up its fuel. These stars are like the diligent misers of the cosmos, using their hydrogen very sparingly and glowing gently for eons. If you were near a red dwarf, the light would be dimmer and redder than our sun, but it would be steady and enduring. Planets around such a star could experience a sun that remains almost the same for potentially hundreds of billions of years, a practically eternal afternoon by human standards. Red dwarfs teach us that not everything in the universe happens on short time scales or in dramatic bursts. Some things last and last in cosmic peace, outliving galaxies, and perhaps even witnessing the distant future eras of the universe. High in the night sky during winter in the northern hemisphere, the constellation Orion stands out. At one shoulder of Orion shines a reddish star named Betelgeuse. Betelgeuse is a red supergiant, an enormous bloated star nearing the end of its life. It's so large that if you placed it where our sun is, Betelgeuse would extend past the orbit of Mars, engulfing Mercury, Venus, Earth, and Mars inside itself. Betelgeuse is cooler than the sun, hence its red hue, but its sheer size makes it extremely bright. It's also a somewhat variable star. Its brightness waxes and wanes over time. Someday, perhaps not too far in the future astronomically, maybe within the next 100,000 years, which is soon for stars, Betelgeuse will likely explode as a supernova. When it does, it will probably be visible in our daytime sky for weeks, and at night it could cast shadows on Earth. But for now, Betelgeuse remains a gentle giant, shining with a steady ruby light. It's a distant swollen star, pulsing and slowly changing, almost like a cosmic heartbeat in the Orion constellation, quietly marking the final stages of a stellar life.
When a star like Betelgeuse eventually goes supernova, it will perform a final act of cosmic alchemy. In its death throes, the star will create and scatter many of the heavier elements that we know, the same elements that make up our world and even our bodies. The calcium in your bones and the iron in your blood were forged in a supernova that occurred billions of years ago, before our sun was born. Those elements mixed with clouds of gas and dust that later coalesced into our solar system. So we truly carry the stardust of ancient stars within us. It's a gentle thought that the universe recycles its matter. The violent end of a massive star, as silent as it may be in the vacuum of space, seeds new beginnings elsewhere. Out of the debris, new stars will form, new planets, and eventually life. In a way, supernova are nature's way of sowing the elements of life across the galaxy, ensuring that each generation of stars contributes to the richness of the cosmos. While the event itself is sudden and dramatic, It unfolds into a long legacy of quiet formation and growth in its aftermath, much like a forest fire that, after its blaze, leaves behind fertile soil for new saplings. In the year 1054 AD, observers in China and elsewhere noted a mysterious new star in the sky. It was visible even in the daytime for a while and then slowly faded over the months. They were witnessing a supernova, the explosive death of a star. Today, in the place where that guest star was seen, we find the Crab Nebula. The Crab Nebula is an expanding cloud of gas and dust, the remains of that long-ago supernova. Through a telescope, it looks like a faint, oval smudge with filaments running through it. At its center lies a rapidly spinning neutron star, a pulsar left behind by the explosion. The Crab Nebula is like a cosmic rose, petals of gas blossoming outward from a central stem. It's quietly expanding at about 1,000 miles per second, which seems fast, but from our vantage point, it changes slowly over human lifetimes. Looking at it is a bit like looking at history frozen in time. It's the echo of a star's death throes from almost 1,000 years ago. And it will continue to drift apart, a gentle expansion for thousands of years to come, gradually mixing with the interstellar medium. It's a beautiful example of how something can transition from a sudden bright flash to a long, enduring presence that astronomers can study centuries later, a kind of gentle afterglow of a dramatic event. Long before there were stars or galaxies, the universe began in a hot, dense state nearly 13.8 billion years ago, an event we call the Big Bang. For the first few 100,000 years, the universe was an extremely bright, glowing plasma, like the inside of a star. As the universe expanded, it cooled down. Eventually, around 380,000 years after the Big Bang, it cooled enough for atoms to form and for light to travel freely for the first time. That light has been traveling ever since, growing fainter and shifting to lower energies as the universe expands. Today, we detect it as a very soft glow of microwaves coming from every direction in the sky, the cosmic microwave background. It's incredibly cold now, just 2.7 degrees above absolute zero. If we could see microwaves with our eyes, the entire sky would look slightly aglow with a uniform faint light. This is literally the afterglow of creation, a gentle bath of radiation that fills the cosmos. It doesn't harm us, it's been with us since the beginning, a sort of peaceful reminder of our universe's fiery infancy now calmed and stretched into a whisper of its former self. When you tune an old radio to an empty frequency and hear static, a small part of that hiss is actually the ancient echo of the Big Bang, now just random noise. So even in the quiet of night, the universe's first light is all around us, serenely present as a low hum in the dark. Our universe has been expanding since its birth in the Big Bang, and from measurements of distant stars and galaxies, we understand that about 13.8 billion years have passed since that beginning. Thinking about such a time frame can be mind-boggling. Billions of years are far beyond human experience. Yet the age of the universe gives us a sense of the grand timescales at play. When we look at very distant galaxies, we see them as they were billions of years ago, because their light has taken that long to reach us. The farther out we look, the further back in time we see. Some of the faint smudges in deep space images are galaxies seen when the universe was only a few billion years old, baby galaxies forming stars rapidly. By studying them, we can quietly read the universe's history like chapters in an ancient book, and as immense as 13.8 billion years sounds, in a way it's also a comfort. It's the age of everything we know. All the stars, all the nights and days on all the planets that have ever existed have taken place within these billions of years. The cosmos unfolds on a schedule so vast that our own lifetimes, while incredibly brief in comparison, are happening right on time in this ancient, ongoing story. While the universe is unimaginably old and vast, there is a limit to what we can see of it. we call that the observable universe. It's essentially the sphere around us from which light has had time to reach us since the universe began. That radius is about 46 billion light-years because the universe has been expanding all the while, so the farthest things we see are now much farther than 13.8 billion light-years away. So the observable universe is a sphere about 93 billion light-years across, centered on us simply because of the travel time of light. Beyond that horizon, there are certainly more galaxies and stars, but their light hasn't arrived yet. Within our observable patch, astronomers estimate there are at least 100 billion galaxies. Each galaxy contains billions or trillions of stars of its own. The vastness of space is almost beyond imagination. Yet, thinking of that number of galaxies can also oddly instill a sense of camaraderie with the cosmos. We are one of many. And just as we have a limited horizon, so would any observer in any galaxy. Each one might think they are in the center of an observable universe as well. It's all a matter of perspective. The important thing is that even though the universe is overwhelmingly large, we can understand it bit by bit, and it remains comprehensible. We find structure, galaxies, clusters, filaments, and that gives us anchor points in the sea of worlds. It's both humbling and soothing to see the order and vastness laid out together. Galaxies come in various shapes and sizes. Some are beautiful spirals like our Milky Way, with graceful arms curving outward from a central bulge, and often rich in gas and dust where new stars are born. Others are elliptical, more like huge balls or ellipsoids of stars, lacking the distinct structure of spirals, and often composed of older, redder stars. And some are irregular, without a clear form, often small or sometimes distorted by gravitational encounters. Each type has its own character. Spiral galaxies can look like cosmic pinwheels or whirlpools. Elliptical galaxies can resemble soft-glowing orbs. Irregular galaxies show that not everything in space is neat. Some are messy, scattered collections of stars. Our night sky mostly shows us stars within our own Milky Way, but when we train telescopes on other galaxies, we see this rich menagerie. The variety in galaxy shapes is like different kinds of cities in the universe, some sprawling and structured, some compact, some chaotic. It suggests that each galaxy has its own history, perhaps past collisions or periods of active star formation or quiet aging. In the still darkness, galaxies float and slowly evolve over eons, each a little ecosystem of stars with its own story written in its shape. The Milky Way is a spiral galaxy with a central bar structure. Our solar system is located in one of its spiral arms about 26,000 light-years from the galactic center. If we could rise above the Milky Way and look down, it would appear as a broad disk with a bright center and spiral arms wrapping around. But from our position inside it, we see it as that milky band across the sky. Our galaxy is rotating. Our Sun and all its planets are moving around the center of the Milky Way at about 500,000 miles per hour. Yet, because the galaxy is so vast, it takes roughly 230 million years to go around once. So since the time of the dinosaurs' emergence, our Sun has made maybe one full orbit around the galaxy. In the grand scheme, the Milky Way is stable and unhurried. Its stars, including our Sun, orbit calmly, like boats on a very smooth, slow-moving carousel. Occasionally, stars do drift a bit or get perturbed by passing ones, but on the whole it's a massive, organized system. When you look up at the Milky Way arching overhead, you can remember that you're seeing the combined light of billions of stars in our neighborhood. We're inside a giant glowing disk, and that hazy band is our panoramic view of home. It's a comforting communal thought. We share this galaxy with so many stars, and presumably many planets, all bound together by gravity, circling a common center in a great cosmic family. Our entire solar system orbits around the center of the Milky Way. It takes about 230 million years to complete one orbit. Sometimes this is referred to as a galactic year. The last time we were at our current location in our orbit around the galaxy, dinosaurs roamed the Earth, and our species wouldn't appear for an unimaginable span of time after that. It puts into perspective the fleeting nature of human history compared to cosmic cycles. Right now, as we're cozy here, our solar system is journeying through the galaxy, currently in a spiral arm region, and will continue onward, perhaps one day drifting to another arm or experiencing the gentle tides of passing near a gas cloud or star cluster. But these shifts happen over tens of millions of years. In any human time frame, the stars around us, the ones that make up the familiar constellations, hardly move at all relative to each other. The patterns in the sky have stayed almost the same throughout recorded history. That gives the night sky a feeling of permanence and steadiness, even though underlying it is this vast orbital motion. It's like how the hour hand of a clock seems still if you watch it moment to moment, but over the course of hours, you notice it has moved. Our position in the galaxy changes so slowly we'll never notice, but over cosmic times it certainly does change. Knowing this, you can appreciate each quiet night under the stars as a momentary view on an ever so slowly changing cosmic panorama. We're on a grand ride, and we don't even feel it, a testament to the smoothness and scale of galactic dynamics. There are at least 100 billion galaxies in the observable universe. Each galaxy contains billions or trillions of stars. Such numbers are hard to grasp. But imagine for a moment the darkest patch of sky you can find. It might look empty to your eyes. The Hubble Space Telescope once stared at one such empty patch for 10 days, collecting any light that came in, and produced the Hubble Deep Field image. In that single tiny speck of sky, it revealed thousands of galaxies of all shapes and sizes, each one an entire galaxy in what looked like nothingness. Multiply that tiny patch by the whole sky, and you begin to appreciate the bounty of galaxies out there. In each of those galaxies, there could be hundreds of billions of stars, and around many of those stars planets. The scale of it is both humbling and oddly reassuring. We occupy one little corner of a vast expanse, and while we might never reach those other galaxies, knowing they exist can feel like being surrounded by a quiet multitude of communities far away. They're too distant to affect us. The nearest big galaxy, Andromeda, is still 2.5 million light-years away, but they add to the richness of existence. The universe isn't an empty void with just a few points of light. It's teeming with these enormous star cities. And even though each galaxy is isolated by huge distances, we connect with them by receiving their light. When we build bigger telescopes, we see farther and gather more of this ancient light. So as you lie peacefully, consider that above you, beyond the stars you see, lie uncountable galaxies, each shining and evolving on their own, their combined light faintly bathing the universe in a dim glow. We're never truly alone in space. We're part of an almost boundless tapestry of galaxies, stretching in every direction. Galaxies often interact and collide. When our Milky Way merges with Andromeda in the far future, the result will be a new, larger galaxy, sometimes nicknamed Milkomeda. But even right now, galaxy interactions are happening elsewhere. Some galaxies are tearing material from others, some are passing through each other, and some have already merged. These events can take hundreds of millions of years to fully play out, so we usually see them in snapshots, one galaxy with a distorted shape, or two connected by a bridge of stars. Our local group is relatively quiet at the moment, but our Milky Way is actually cannibalizing some tiny dwarf galaxies as we speak, pulling them apart with tidal forces. These interactions are part of the growth of galaxies. Small ones merge into bigger ones over time. And when big ones collide, their shape often transforms. Spirals can turn into ellipticals, for example. It sounds dramatic, and on a grand scale it is, but again, from a star's perspective within those galaxies, it's like two clouds blending, largely peaceful locally. Still, imagine the night sky on a planet in a galaxy that's in the midst of merging with another. You might see an astounding number of bright stars,
or a band of new light across the sky from the other galaxy's stars. It could be both beautiful and disorienting. Here on Earth, in a few billion years, future beings might see Andromeda gradually spreading across the sky until it fills it, then the chaos of different patterns of stars as the two galaxies settle together. But that's a long, long way off. For now, the Milky Way and Andromeda face each other across a gulf of space, moving imperceptibly closer each year. It's a reminder that nothing in the universe is static. Given enough time, even galaxies find new partners and change. The universe evolves, yet it does so on timescales so immense that it's perfectly fine for us to appreciate the serenity of the status quo. Our galaxy's arms will continue to turn gently, and Andromeda's gentle glow will remain a fixed presence in the sky for all of human existence and beyond, until that far-off future dance begins. Even when galaxies collide, stars within them mostly miss each other. But that doesn't mean nothing happens. One significant consequence of galaxies interacting is that they can trigger bursts of star formation. Picture two galaxies passing through one another. Their gravitational forces tug and compress clouds of gas in each galaxy. As those clouds get compressed, they can collapse and fragment, forming many new stars in a relatively short period of time, astronomically speaking. These are called starburst events. So rather than collisions destroying things, in space they often create new stars. These newborn stars can be very massive and luminous, lighting up the regions where they form and creating spectacular nebula. After an interaction, a galaxy might be littered with clusters of young blue stars, like cosmic fireworks that went off during the encounter. Over millions of years, those hot young stars will burn out, some as supernova, and things will calm down again. It's almost as if galaxies have a heartbeat, normally slow and steady, but when something exciting happens, like a close interaction, the pulse quickens with a flurry of activity then subsides. If you think of the universe as largely calm and stable, that's mostly true. But here and there for a while, it's like a spring bloom in a forest after a disturbance, lots of rapid growth before returning to quiet. Right now, our Milky Way is not in a starburst phase. It's forming stars at a modest rate. But some galaxies we observe, especially ones we catch in the act of colliding, are undergoing intense starbursts. They shine brightly in infrared, as dust warmed by new stars radiates heat. They're lovely in their own way, but also somewhat chaotic. Ultimately, they too will quiet down, as the new stars settle and the gas is used up. Thus the cosmos balances periods of calm and activity, even in the life cycles of galaxies. Beyond our solar system, we have discovered thousands of exoplanets, planets orbiting other stars. These worlds come in astonishing variety. Some are gas giants larger than Jupiter, that orbit closer to their stars than Mercury does to our Sun, so-called hot Jupiters. Some are super-Earths, which are rocky planets a bit bigger than our Earth. We have found planets in multi-planet systems, where they have orbital resonances, meaning their gravities tug periodically in a harmonious way. We've found planets around pulsars, which is surprising, as pulsars are neutron stars left from supernova. Those planets may be the shattered remnants of the star's original system. It seems that nature loves to make planets. Wherever there's a star, there's a good chance there are planets around it. It's incredible to think that the pinpoints of light in the night sky, the stars, are often accompanied by their own tiny pinpoints of nature, circling around, perhaps with atmospheres, maybe even with moons of their own. Our galaxy likely holds billions upon billions of planets. Some of those might be barren, some might be gas envelopes, but some could be Earth-like. The Kepler Space Telescope and other surveys have shown that small rocky planets in the habitable zone are not rare. So as you lie here, under a blanket of stars, reflect that under many of those stars are worlds. Worlds with sunsets and perhaps mountains or oceans of their own. It expands the imagination. Maybe someone or something there is looking back, or maybe those worlds are as quiet and still as the scene you see here, waiting for life or just peacefully existing without it. Either way, the proliferation of exoplanets tells us that making planets is a natural part of star formation. We aren't an outlier. We're part of the vast and varied family of planetary systems spread throughout the Milky Way, each one turning in the gentle light of its parent star. Some exoplanets lie in their star's habitable zone, where temperatures could allow liquid water on their surfaces, a key ingredient for life as we know it. One such planet is Kepler 186f, which is only slightly larger than Earth and orbits a red dwarf star, about 500 light-years away. It receives about a third of the light Earth does, but because its star is cooler and redder, the light spectrum is different. If Kepler 186f has an atmosphere, the sky might be a hazy crimson during the day under a dim sun. We don't know if it has water or an atmosphere, but its existence shows that Earth-sized planets exist in Earth-like orbits.
Another interesting system is TRAPPIST-1, about 39 light-years away. This star is an ultra-cool dwarf, and it has 7 known planets, 3 of which are in or near the habitable zone. Because the star is so dim, the habitable zone is extremely close to the star. Those planets have years that last just a few days. They're likely tidally locked, meaning one side always faces the star and one side is in perpetual night. If any of them have an atmosphere, winds would redistribute heat, and perhaps the most comfortable region would be around the edges of the day side, where it's eternal twilight. It's fascinating to imagine standing on one of those planets. The star looms large and red in the sky, bigger than our sun looks, but much dimmer, and nearby you'd see other planets in the sky, possibly as large crescents because they're all close together. That sky could have multiple moons, actually sister planets, visible. It would be a very alien, but potentially beautiful environment. These discoveries spark our hope that maybe life has more opportunities out there. But even without going that far, just knowing these planets exist can make one feel a sense of kinship across space, little Earth-like worlds scattered through the galaxy, all cold and dark right now as far as we can tell, but each perhaps as tranquil as our own world's quiet, pristine places. Not all exoplanets are ordinary worlds. Some are quite exotic. There's an exoplanet called 55 Cancri e, so close to its star that its year is less than 18 hours. It's a rocky planet about twice Earth's size and 8 times Earth's mass. Being so close to its star, one side of it is extremely hot, around 2,400 degrees Celsius or 4,400 degrees Fahrenheit, while the far side is much cooler, likely tidally locked with a permanent day side and night side. For a time, scientists speculated its composition might be carbon-rich, perhaps even with a mantle full of diamond if the conditions were right, hence its nickname as a diamond planet. Whether or not that's true, it's certainly a bizarre place. The daylight side might have lava flows or an ocean of molten rock, and the night side could be cool enough for some of that rock to solidify. Imagine a world where the sky is probably a hellish glow on one side and star-studded black on the other, with a stark Terminator line where day meets night, maybe swirling with storms generated by the temperature difference. In our own solar system, we have unusual moons, like Io with its volcanoes or Europa with its ice crust over an ocean. Exoplanets extend that diversity. One planet, HD 189733b, a hot Jupiter, is so hot that it might rain molten glass sideways in ferocious winds. The atmosphere contains silicates, which could condense into glassy droplets in the cooler upper atmosphere and get blown horizontally by 4,000 miles per hour winds. It sounds violent, but if you were somehow floating there protected in a capsule, say it might look like shimmering blue rain whipping by at insane speeds. Beautiful in concept, terrifying in reality. These extreme worlds underscore how gentle and mild our own planet is by comparison. Earth's conditions are just right to cradle life comfortably. Many other places are far less hospitable. So when you savor the calm of an earthly night, it's worth appreciating how uniquely kind our environment is. In contrast to these far-off curiosities that show just how creative the universe can be with planets. There may be rogue planets floating alone in the dark of space, not orbiting any star. These free-floating worlds likely formed in a star system but got tossed out by gravitational interactions, or a few might have formed from gas clouds that were not massive enough to ignite as stars. In the darkness of interstellar space, a rogue planet would be a lonely place. Without a sun, its sky would be black, peppered with stars as seen from any planet, but no single bright sun. The planet's own heat, from its formation or radioactive elements, might provide some warmth, and if it had enough atmosphere or geothermal activity, it could possibly retain pockets of liquid under ice. It's speculative. But scientists wonder if rogue planets could even harbor life in such isolated environments, perhaps under an insulating ice shell warmed by a planetary core, as some moons in our solar system have subsurface oceans. Even if not, rogue planets are intriguing. They drift through the galaxy's gravitational fields, perhaps occasionally passing near a star and then heading back out. One could wander into our solar system someday, though we'd likely detect it far away if so. Conversely, our system may have ejected planets in the past. These orphan planets roam the galaxy unseen except by the slight gravitational effect they have when passing by something, or if a distant star briefly lenses behind them. Imagine being on one eternal night, stars barely moving over millennia, cold and still. It might snow or rain depending on the atmosphere, but no sunrise ever. It's a scene of ultimate solitude. Yet, if you look up, you'd see the Milky Way band, assuming you're not too far out of the galactic disk, and that could be your only source of gentle light, the combined glow of distant stars too far to reach. So even a rogue planet is not entirely alone. It has the distant glow of the galaxy to keep it company. The existence of such worlds reminds us that orbits so reliable for us can be disrupted, but even in disruption there can be a sort of peace, a lone planet, with perhaps a moon or two still bound to it, taking a solitary journey through the quiet between the stars. At our Milky Way's center, there's a giant cloud of gas and dust where chemists have detected a molecule called ethyl formate. Interestingly, this chemical is responsible for the flavor of raspberries and the scent of rum. Of course, space isn't filled with these smells in a way we could notice, and the concentrations are incredibly low and mixed with other things like alcohols and cyanides. But it's a whimsical footnote that something out there shares a connection with familiar tastes and smells. If you could somehow take a scoop of the gas from the middle of our galaxy and analyze it, you'd find a variety of organic molecules, not life, but the raw ingredients. There's something poetic about that. The center of our galaxy has a hint of sweetness and spirits as described by that discovery. More broadly, the universe is a great chemist. Nebulae between the stars are like vast laboratories where atoms and molecules bump and join. They produce not just simple things like hydrogen and helium from the Big Bang, but complex organic molecules, from simple alcohols to amino acids, the building blocks of proteins. These float around and eventually get incorporated into new stars and planets. So the seeds of life's chemistry are everywhere. The next time you catch the smell of rain or the aroma of fruit, consider that the elements and compounds involved have cosmic origins. In a way, Earth's biosphere is nature's way of concentrating and organizing these chemicals that were dispersed in space. It's heartwarming and calming to think that the galaxy and our planet are not separate in composition. We are made of that star stuff and space stuff. So the little coincidence that the galaxy smells like raspberries is a cute reminder of our connection. As you inhale the cool night air, you can relish that you're breathing oxygen that was forged in a star and nitrogen that came from a stellar explosion. Everything has a history. And out there, 26,000 light-years away in the galactic core, a cloud quietly brews compounds that, here on Earth, we find pleasant and familiar. Distant galaxies appear to be rushing away from us, their light stretched to longer, redder wavelengths, a phenomenon called redshift. This is evidence of the expanding universe. Space itself is stretching, carrying galaxies apart. But this expansion isn't something we feel or notice locally. It's so minuscule on small scales that atoms, people, planets, even galaxies don't expand because their own gravity or forces hold them together. It's only obvious when you look across millions of light years. One way to imagine it is like raisin bread dough rising. The raisin's galaxies move apart as the dough space expands, but the raisins themselves don't change size. If you were on a raisin, you might not sense the rising, but you'd see others getting farther. So from our perspective on Earth, almost every distant galaxy's light is redshifted, aside from a few nearby ones bound to us by gravity, like Andromeda, which is blue shifted. The farther a galaxy is, the faster it seems to recede, and the more its light is redshifted. When you look up at the sky, you can't see this without special instruments. The stars and galaxies look as they are at the moment their light left them. But that light is imbued with the story of the journey. A photon from a galaxy a billion light-years away might have started out as blue light and arrived as red light, stretched en route. Cosmologists find this one of the most profound truths, that the universe is dynamic, not static. And what's more, as we learned, this expansion is accelerating because of dark energy. But on a clear night, everything seems serene and fixed. The stars don't obviously rush away. That's the charm. The universe can be doing something astonishing, like expanding in a way that's utterly gentle and imperceptible in our daily experience. It's a lesson that big truths don't always announce themselves loudly. Sometimes they're subtle, encoded in faint changes in color, or the positions of distant galaxies measured carefully over time. Yet the result is the grand narrative. The universe has been growing from a hot, dense state to the spacious quilt of galaxies we see now, and it continues to do so, without hustle or noise, just a steady, inexorable stretching that has been going on for billions of years. Gravity can bend light like a lens. Massive objects like galaxy clusters warp the space around them, causing the light from more distant galaxies behind them to be distorted, magnified, or even appear multiple times. This phenomenon is known as gravitational lensing. It's as if space itself were made of a flexible material that a heavy object can indent. When light passes near that indentation, it curves. The result is that we sometimes see strange mirages. A distant quasar might appear as two identical quasars close together, but it's actually one object whose light is being split into two images by a galaxy's gravity in the foreground. There are instances of Einstein rings, where a background galaxy's image is stretched into a perfect or near-perfect ring around a foreground galaxy. These are not only useful for astronomers to study distant galaxies and to map dark matter in the lensing object, but also visually enchanting. They're like cosmic smiley faces or jewelry hidden in the sky, unless you have a powerful telescope. If you think about it, gravitational lensing means that sometimes when we're looking at the sky, some of the light reaching us has taken a curved path through space, detouring around a mass to reach our eyes. But we'd never know without careful study. It just appears a bit out of place or multiplied. It's a very gentle effect, nothing violent, just the graceful curving of space itself. In daily life we don't see this because we need huge masses and huge distances, but it's happening out there silently.
Gravitational lensing is also a reminder of Einstein's insight that mass and energy tell space how to curve, and space tells matter and light how to move. The universe has a beautiful geometry to it. When you see the stars, you see them mostly as they are, but in the background, faint and subtle, are these distortions, like the gloss on a painting. They don't ruin the picture, they're part of it. They even allow us glimpses of things we otherwise couldn't see by magnifying distant galaxies. So the universe itself provides telescopes for us. In the form of massive clusters, it's a cooperative gesture from nature, allowing us to peer a little deeper into the cosmos through the natural warp of space. Time itself flows differently in strong gravity. Near a massive object like a black hole, time runs slower compared to far away, an effect of general relativity. Similarly, if you're moving very fast, time also slows for you relative to others. That's special relativity. These effects are usually tiny in everyday situations, but they become significant in extreme cases. For example, GPS satellites have to correct for time dilation due to both their speed, which makes their clocks run slow by a tiny bit, and being higher up in Earth's gravitational field, which makes their clocks run fast by a tiny bit. The combination is that they tick a little faster than ground clocks, and engineers account for that to keep GPS accurate. In sci-fi scenarios, someone who travels near a black hole and comes back might find that more time passed for everyone else than for them. In a sense, that's a form of time travel to the future. One can skip ahead by experiencing less time. But for the person in that scenario, nothing odd happens. They don't feel time slow. They feel normal, and it's everyone else who would seem sped up if they could observe them. It's only upon reunion you see the difference. This tells us time is relative, bound up with space and motion. What a calm and wondrous universe that such a thing can be true. Yet our everyday lives proceed normally because we're usually in similar gravitational fields and moving at similar slow speeds. Imagine orbiting a black hole safely at some distance. You might see the outside universe's events going faster if you could see them. Stars aging quickly, etc. While you experience, say, a year, you come back and far more time has passed outside. It's a bit eerie and poignant. It makes us realize we can never think of time in absolute terms, always consider the frame of reference. Yet for all practical purposes on Earth, time feels uniform and absolute, a steady tick. That's another duality of understanding. The universe has these flexible time and space properties, but we live in a nook of it where things are gentle and stable enough that Newtonian ideas work just fine for day-to-day living. Time dilation is going on right now. Clocks on a mountain tick a tiny bit faster than clocks at sea level due to weaker gravity. But you'd need atomic clocks to notice. In a way, it's comforting that the universe has these protections in place. You won't suddenly have a day that is an hour longer just because you moved. Changes are continuous and extremely small, unless under extreme conditions, which we avoid for safety. So, as you drift to sleep, you can trust that tonight, seconds will march on as usual. In dreams we may distort time subjectively, but out here, in our gentle corner, time will keep a steady lullaby pace. White holes are theoretical opposites of black holes. Where nothing can escape a black hole, nothing can enter a white hole. It can only spew things out. They appear in certain mathematical solutions to Einstein's equations, essentially running a black hole solution backwards. While intriguing on paper, there's no evidence they exist in nature. Some have mused, could the Big Bang itself have been a kind of white hole? Or could black holes in some way connect to white holes elsewhere, as in a wormhole scenario? These ideas remain speculative. If a white hole did exist, what would it look like? Perhaps a sudden outpouring of matter and light from a point in space, with no obvious source, like a film of a black hole swallowing something but in reverse. If you encountered one, you couldn't enter it. It would push you away with emitted matter or energy. However, any white hole solution in the real universe seems unstable, slightest perturbation, and it collapses into a black hole or something else. So, likely, white holes are just a mathematical curiosity. Yet they remind us of the symmetry in physics. Often if something can go one way, equations suggest it can go the reverse. Nature usually has a preferred direction, like time's arrow from past to future, or entropy increasing. So not everything symmetric exists, but it's delightful to think about. The universe as we know it seems to have started in a low entropy state and moves to higher entropy, making one-way processes common like eggs breaking but not unbreaking. A white hole would violate that trend dramatically. It'd be like an egg assembling itself unbroken on the floor. So probably not happening. But as a gentle bedtime musing, white holes are like the dream version of black holes, mirror images that might appear in some alternate reality, but not ours. The takeaway is that for now, everything we see acts as expected. Stars shine by burning fuel, not by magically having fuel appear inside them from nowhere, which a white hole might analogously do, and black holes only ingest. The stability of the cosmos relies on such consistency. White holes remain a fun concept that prompt what else might be possible that we just haven't thought of or found. The universe likely has more surprises, though maybe not white holes. Still, it costs nothing to imagine them as you drift off. Cosmic fountains of creation, balancing in theory the sinks that are black holes. In reality, we content ourselves with stars and galaxies, which already give us more than enough wonder. When massive objects like black holes or neutron stars collide, they send out ripples in space-time called gravitational waves. These waves travel at the speed of light, gently stretching and squeezing space as they go. They are incredibly faint by the time they reach Earth, because by then they've spread out over vast distances. But in 2015, the LIGO Observatory detected gravitational waves directly for the first time, from two black holes merging about 1.3 billion light-years away. The signal was a tiny oscillation, matching predictions almost exactly, a rising chirp frequency as the black holes spiraled together faster and faster, then a quick drop-off after they merged into one larger black hole, which then rang briefly and settled. It was such a tiny movement, something like a fraction of a proton's width change over kilometers of distance, yet we built instruments sensitive enough to see it. It confirmed a piece of Einstein's theory 100 years after he predicted it, and also opened up a new window to observe the universe. Since then, gravitational wave detectors have heard several black hole mergers and even a couple of neutron star collisions. The neutron star collision in 2017 was especially exciting because telescopes also caught light from it, a flash called a kilonova. That event made heavy elements, a lot of gold and platinum, for instance, were forged in that single collision and flung into space. Gravitational waves themselves don't pose any harm to us. They pass through us all the time from distant cataclysms. But they're so weak by the time they arrive that we're unaffected. It's like being on a calm lake, but learning that an imperceptible ripple just passed by that originated from a stone thrown in a pond on the other side of the world. Now that we can detect them, it's like we've attuned our ears to the cosmic symphony. Before we only saw the light. Now we can also feel the tremors. Together they give a fuller, richer picture, like seeing lightning and hearing thunder. Except these thunderclaps are utterly silent to our ears, and only audible to ultra-sensitive instruments. As you lie still, know that space-time around you is serene, but subtly minutely quivering from distant events. Perhaps a pair of black holes coalesced in a galaxy far away right this moment, and in some years that wave will pass us and ever so slightly rock us in our sleep, unbeknownst. The universe has its background music, a very bass, deep rhythm to accompany the twinkling lights.
Still, it costs nothing to imagine them as you drift off cosmic fountains of creation, balancing, in theory, the sinks that are black holes. In reality, we content ourselves with stars and galaxies, which already give us more than enough wonder. When massive objects like black holes or neutron stars collide, they send out ripples in space-time called gravitational waves. These waves travel at the speed of light, gently stretching and squeezing space as they go. They are incredibly faint by the time they reach Earth, because by then they've spread out over vast distances. But in 2015, the LIGO Observatory detected gravitational waves directly for the first time from two black holes merging about 1.3 billion light-years away. The signal was a tiny oscillation matching predictions almost exactly, a rising chirp frequency as the black holes spiraled together faster and faster, then a quick drop-off after they merged into one larger black hole, which then rang briefly and settled. It was such a tiny movement, something like a fraction of a proton's width change over kilometers of distance, yet we built instruments sensitive enough to see it. It confirmed a piece of Einstein's theory 100 years after he predicted it, and also opened up a new window to observe the universe. Since then, gravitational wave detectors have heard several black hole mergers and even a couple of neutron star collisions. The neutron star collision in 2017 was especially exciting because telescopes also caught light from it, a flash called a kilonova. That event made heavy elements, a lot of gold and platinum, for instance, were forged in that single collision and flung into space. Gravitational waves themselves don't pose any harm to us. They pass through us all the time from distant cataclysms, but they're so weak by the time they arrive that we're unaffected. It's like being on a calm lake, but learning that an imperceptible ripple just passed by that originated from a stone thrown in a pond on the other side of the world. Now that we can detect them, it's like we've attuned our ears to the cosmic symphony. Before we only saw the light, now we can also feel the tremors. Together they give a fuller, richer picture, like seeing lightning and hearing thunder. Except these thunderclaps are utterly silent to our ears and only audible to ultra-sensitive instruments. As you lie still, know that space-time around you is serene, but subtly, minutely quivering from distant events. Perhaps a pair of black holes coalesced in a galaxy far away right this moment, and in some years that wave will pass us and ever so slightly rock us in our sleep, unbeknownst. The universe has its background music, a very bass, deep rhythm to accompany the twinkling lights. To grasp how small we are in the galaxy, analogies can be useful. Here's one: if the sun were the size of a single white blood cell, which is microscopic, then the Milky Way galaxy would be about the size of the continental United States. Or another, imagine the solar system out to Neptune as a coffee cup. On that scale, the Milky Way would span the Pacific Ocean. These comparisons highlight that even though the solar system feels huge to us, with years-long journeys to the outer planets, it's a tiny pocket of our galaxy. And our galaxy is just one of billions in the local supercluster, and so on. We can also reverse the perspective. If an atom were blown up to the size of the solar system, the nucleus would be like a grain of sand in the middle, and the electrons like dust motes whirling at the edges, mostly empty space. So whether we go up or down in scale, there's a lot of emptiness and a lot of surprising size differences. But focusing on the cosmic side, our Earth is a small rock orbiting a star that is 1,000,000 times smaller in volume than the Sun, and the Sun itself is one of hundreds of billions of stars in the Milky Way, and the Milky Way is one of 100 billion or more galaxies in the observable universe. Does that make you feel insignificant? Perhaps, but it can also be a relief. The universe is not all on our shoulders. The problems and dramas of our lives, while very real to us, don't disturb the stars. There's a stable backdrop that continues regardless. You can take comfort in the continuity of cosmic cycles. The sun will rise, Earth will spin, the galaxy will turn all on scales that dwarf human worries. At the same time, we're part of this grand tapestry. Our atoms come from stars, and our awareness makes the universe conscious of itself in a way. As the astronomer Carl Sagan famously said, "We are a way for the cosmos to know itself." That's a profound thought to settle into in all that vastness. We emerged and can ponder it. No, we can't alter the orbits of stars, nor do we need to, but we can appreciate them. We carry a bit of the universe's story within us, literally stardust and cosmic history encoded in us. So rather than feel lost, you might feel found, connected to something so much bigger. Float on that feeling of belonging to the universe. Yes, compared to it we are small, but we are also unique in our capability to witness it. And that gives our small size a luminous significance. The farthest human-made object, Voyager 1, has been traveling for over 45 years and is now over 14 billion miles away, in interstellar space beyond our solar system. It carries a golden record with sounds and images of Earth, laughter, music from different cultures, greetings in many languages, the sounds of wind and surf and animals, and encoded pictures of people, places, and even DNA. It's a time capsule intended for whoever might find it in the distant future, even if that's millions of years from now. The chances are slim that anyone will intercept Voyager 1, but just the act of sending it is a hopeful gesture. Voyager 1 and its twin, Voyager 2, show what humanity can do with ingenuity and curiosity. Originally, they were designed to tour the outer planets, which they did spectacularly, sending back breathtaking images and discoveries, like volcanoes on Jupiter's moon Io, and the delicate structure of Saturn's rings, and the icy geysers on Neptune's moon Triton. After completing their main missions, they just kept going, coasting outward. They taught us where the sun's influence ends. Voyager 1 detected the heliopause, where the solar wind's particles give way to the interstellar medium. Now these probes will continue drifting. In about 40,000 years, Voyager 1 will pass relatively near another star, not super close, but within a couple light years. Even then, it's unlikely it will be spotted. Space is huge and Voyager is tiny. It will likely wander the galaxy for millions, even billions of years. Eventually, its radioisotope power source will die, it's almost out already, and it'll be an inert piece of metal and golden plating silently traversing the emptiness. In that sense, Voyager 1 is like a message in a bottle cast into a vast ocean. Perhaps no one finds it, or perhaps someday far, far in the future, an alien civilization or our own distant descendants with advanced tech might stumble upon it and marvel at the old artifact. It's a comforting thought that a piece of us is out there beyond the sun's domain, moving through the starlight between the stars. It's as if a part of humanity's spirit, our curiosity and goodwill, has been set free among the stars. And as lonely as Voyager is, it carries voices and music, encapsulating a piece of our world's soul. So in a way, we're out there too, riding along. And in the quiet of a night you can whisper a good wish to Voyager and beyond. It's out there under the same stars, forging ahead in the dark for all of us. As you finally let your eyes rest and your mind drift, consider this profound connection. Almost every atom in your body was forged in a star. The calcium in your teeth and bones was formed in the heart of a dying star that exploded long ago. The iron in your blood was created in a supernova's fury. The oxygen you breathe was made in a star's fusion process and released when it shed its outer layers. Even the carbon that is so essential to life, and the nitrogen, were crafted in stars. We truly are made of star stuff. We are the universe, in a very real sense, contemplating itself. The atoms that compose you have been on an incredible journey. Some came from ancient supernovae, some from cosmic rays converting atoms in the atmosphere, some from the Big Bang like most of the hydrogen in your body's water. And here they are now, assembled in you, a thinking being. For a time they cooperate as you, and when that time ends, they will disperse and perhaps become parts of other living things, or float in the air, or become part of the soil, eventually perhaps to return to space when Earth itself one day will be altered. But there's no need to think of that with sadness. It's a beautiful cycle of transformation. Nothing is ever truly lost, it only changes form. Right now, the form those atoms take is a person listening to a gentle voice, breathing steadily under the night sky. You are the cosmos, and the cosmos is you. In this moment, the boundary between out there and in you blurs. It's all one grand existence. Feel the peace of that unity. The stars shine down, ancient and knowing, and you shine too, in your own way. Your consciousness is like a brief spark, but it's connected to the eternal lights overhead. So as you ease into sleep, you can let all burdens fall away. You are cradled by the universe, literally, your body by Earth, Earth by the sun's gravity, the sun by the Milky Way's embrace, and the Milky Way by the fabric of space. It's a safe and natural place to be. In the cosmic perspective, every problem finds its context, and every joy is part of the tapestry. Your home in the universe, the stardust in your veins, and the stardust in the sky are of one kind. In this deep understanding, there is serenity. Everything is as it should be, and you are a magnificent though tiny part of it all. And with that knowledge, you can let yourself drift off, secure and connected. In this vast cosmos, on this gentle night, you are part of the stars, and they are part of you. In that timeless unity, you can find comfort and rest. Good night.